Okay, good morning everyone. So in last class we have discussed about the postulates of valency bond theory. So just recall the postulates once again. This valency bond theory is proposed by Holmes, and according to this theory, a covalent bond is present between the central metal atom or ion and ligands. Okay, so up to now we assumed that before this valency bond theory, we assumed that the coordinate covalent bond is present between central metal atom or ion and ligand. But according to this theory, he directed that the coordinate bond. According to this theory, a coordinate covalent bond is present between the central metal atom and the ion. And next see, and when a coordinate covalent bond is going to be formed between the central metal atom and the ligand, so before that, what happens? The central metal atom will provide the vacant orbitals. So the main duty of central metal atom or ion is to provide vacant orbitals. So the number of vacant orbitals always equals to the number of accepting lone pair of electrons. So or we can also say in another word as coordination number. But suppose if coordination number of a compound is 4, that means the central metal atom or ion will taken up 4 lone pair of electrons from ligand. So at that time, that central metal atom or ion need to provide 4 vacant orbitals. Okay. Next, if coordination number is 6, then the central metal atom or ion will taken up 6 electrons from the ligand. At that time, that central metal atom or ion need to provide 6 vacant orbitals. Next, this vacant orbitals later what happens? They may undergo hybridization. So this vacant orbital of central metal atom. Next, what happens? They may undergo hybridization, or we can say rearrangement in other words. So due to hybridization, the importance of valence bond theory is this theory explains the geometry of the complex compounds. So they explain the geometry of the complex compound according to the hybridization of a central metal atom. So for suppose if central metal atom undergo sp hybridization. So in sp hybridization, how many vacant orbitals will overlap? Two vacant orbitals, one s and one p orbital. So that means the central metal atom or ion is going to be accept two lone pair of electrons from the ligand. So that's why it provided two vacant orbitals. And those vacant orbitals, one is from s orbital and one is from p orbital. And now these two orbitals undergo hybridization, and that hybridization is known as sp hybridization. So this sp hybridization imposes linear geometry to the complex compound. Next, second hybridization is sp2 hybridization. So in that sp2 hybridization, how many orbitals are taken part in sp2 hybridization? Three. One from s orbital and two from p orbitals. So that indicates what the central metal atom has provided three vacant orbitals. So thereby it can taken up three lone pair of electrons. Okay. So now these three orbitals, one s and two p orbitals undergo hybridization. That hybridization is known as sp2 hybridization, and this sp2 hybridization imposes trigonal planar geometry to the complex. And next hybridization is sp3 hybridization. In that sp3 hybridization, central metal atom will provide four vacant orbitals, one s orbital and three p orbitals. So that indicates what the central metal atom is going to accept four lone pair of electrons, and the coordination number of that complex compound is 4. Okay. Now this one s orbital and three p orbitals undergo hybridization, and that hybridization is known as sp3. So this sp3 hybridization imposes or imply tetrahedral geometry to the complex compound. And we have one more example. In that also, central metal atom will provide four vacant orbitals. But these four vacant orbitals are different. One is from d orbital, one from s orbital, and two from p orbitals. Okay, total how many? Four. And what are those? One d orbital, one s orbital, and two p orbitals. Now this hybridization is known as dsp2. This dsp2 hybridization imposes square planar geometry to the complex compound. So here see four orbitals. One is sp3, second one is dsp2. Okay, please remind it. Be attentive. Uh, make a note it. Okay, one is sp3 hybridization and second one is dsp2. In both hybridization, it requires how many vacant orbitals? 4 vacant orbitals. But hybridization is different. Whenever hybridization is different, the properties also be different. Properties means geometry, particularly geometry. So geometry, what is the geometry of sp3? Tetrahedral, and dsp2 square plane. Okay. Next come to another hybridization, that is dsp3 hybridization. So in dsp3 hybridization, settled metal atom will provide 5 vacant orbitals. How many? 5. In which hybridization? dsp3. So what will be those? No, those are 1 from d orbital, 1 from s orbital, and 3 from p orbital. And these 5 orbitals undergo hybridization. That hybridization is known as dsp3. And that dsp3 hybridization imposes trigonal bipyramidal geometry to complex compound. Trigonal bipyramidal. In the trigonal bipyramidal, we may have 2 different bond angles. In trigonal, the bond angle between 3 bonds is 120, and the bipyramidal means one the above the plane of trigonal plane, and another bond is below. So one bond exists above the plane of trigonal planar, and another bond, we can say fourth bond above the plane, and fifth bond below the plane of trigonal. And between the bond angle between this fourth and fifth bond is almost 180 degrees. So in trigonal bipyramidal, we may have 2 bond angles. One is 120 degrees, second one is 180 degrees. Whereas in sp3, we know that 109, and square planar, how much? 90 degrees. And sp2, 120, and sp 180. Okay, we know that already in previous classes we have studied about the hybridization and bond angles. And next, and important one is here, see, 5 orbitals. 1d, 1 from s, and 3 from p. So that is known as dsp3 hybridization. And again, we may have another hybridization that is also known as sp3d hybridization. So see, dsp3 hybridization. Second one is sp3 hybridization. So in both hybridization, we require 5 vacant orbitals. So central metal atom will provide how many vacant orbitals? 5 vacant orbitals. In dsp3, second one is sp3d. So see here, see. In first case, the d is coming first, dsp3. So before s, we have d. In second case, d coming after p, sp3d. So first hybridization is known as inner hybridization, and second hybridization is known as outer hybridization. So what is the difference between these 2 hybridations? See here, see, in dsp3, so before s subshell. So what is a quantum? What is, for example, if you consider a 3D 3D transition element. In the 3D transition element, the outermost shell will be the 4. Okay, and before that we may have 3D 4s 4p0, 3D 4s 4p0. So 3D means what we can consider that one as n minus 1. N is the what? Principal quantum number. So that is the principal quantum number of outermost shell in 3D transition state is 4. And this d orbital belongs to inner. Inner means d 4 minus 1, that is 3D. This is 4s. But in case of sp3d, all 3 orbitals belongs to same shell or same energy level. That is 4 energy level. 4s, 4p, 4d. But whereas in inner, one is inner orbital, that is inner d orbital, n minus 1, 3d, and 4s, 4p. Okay, so keep in your mind this. Okay, it is important. And next, inner hybridization, dsp3, outer hybridization, sp3d. So, but both hybridization geometry is one and same, trigonal bipyramidal. And next one is sp3d2, and here one s and 3p orbitals, 1 2d orbitals, total 6. sp3d2 or d2sp3. We have both d2sp3, that is inner hybridization, sp3d2, that is outer hybridization. But in both hybridations, central metal atom will provide how many vacant orbitals? 6 vacant orbitals. And geometry is one and same, that is octahedral again, and the bond angles in octahedral also 2 bond angles we may have. First one is 90 degrees, and second one is 180 degrees. Okay, so with the help of this geometry, hybridization, we can predict geometry or shape of the complex compound. Not only shape, shape of the complex compound, and we can also predict some properties like magnetism or color properties also. Okay, and next one here, see. So inner hybridization and outer hybridization. So that hybridization, who will decide that hybridization? So which d orbital to be taken part or to be take part in hybridization? Who will decide? So that incoming ligand. Here see the basis of field strength of ligands. We have two types of field strength of ligand. One is strong field ligand. Second one is weak field ligand. This strong field ligand promotes the or induces hybridization of inner orbitals. Why? Because by it pair up the unpaired electrons. So it pair up unpaired electrons. So thereby it provides vacant inner d orbital. Which ligands? Strong field ligands. Whereas weak field ligands, they do not have enough energy to pair up the electrons. So thereby it cannot provide vacant inner d orbital. So in this case, in the weak field ligands, they are generally outermost or outer d orbitals participates in hybridization. So the strong field ligand promote inner hybridization, whereas weak field ligands promote outer hybridization. So strong field ligands, again, one more important thing we need to be remembered, that is the strong field ligands pair up the electrons. So whenever the number of unpaired electrons are decreased, so then the spin of that complex compound is low. So that's why we can say low spin complexes. So the strong field ligand promotes inner hybridization as well as low spin. Occur hyperligated complex, and such complex compounds are also known as hyperligated compounds. But whereas weak field ligands that do not pair up the electrons, so thereby the resultant complex compound spin is high. So that's why we can say high spin complex compounds, or you can say outer orbital or outer hybridized orbital. Outer hybridized complex compounds are high spin complex compounds. So which will form weak field ligands, whereas strong field ligands forms or promotes inner hybridization along with that accompanies what? Low spin. Okay, next. One more importance of this complex compound is just now I told you we can predict the magnetism of given complex compound. So actually, magnetism three types in nature. We have five types, but broadly we classify the metals on the basis of its magnetism into three categories. One is the dia, second one is para, third one is ferro. Okay. So, but this Hund theory or VBT theory will classify the complex compounds into two categories, that is paramagnetic and second one is a diamagnetic. Okay. So what is paramagnetic and what is diamagnetic? So this magnetism generally depends on this magnetism is attributed due to presence of due to electrons, particularly the properties of electrons. And what are those? One is spin quantum number, and second one is orbital momentum. Angular momentum. So this spin quantum number or spin momentum is denoted as capital S, and angular momentum is denoted as capital L. But in complex transition metals, this L, the contribution of L or contribution of angular quantum moment towards magnetism is zero. Why? Because the electrons of central metal atom will not be influenced by uh, influenced by uh, ligands. So that's why L is negligible. So that's why due to that the magnetism is purely depends on the spin quantum number of electrons. Okay, the spin quantum number, how we can calculate the spin quantum number? So spin quantum number is nothing but the sum of electrons of orbital. So each orbital can accommodate maximum how many electrons? Two electrons. And the orientation of these two electrons in one orbital is opposite to each other. So that means in one orbital, one electron orients in clockwise. At the same time, the other electron orients in anti-clockwise. And the orientation, the value, spin quantum number, or spin value of electrons. So how we assign? We generally assign plus half and minus half. So plus half to clockwise orientation and minus half to anti-clockwise orientation. So whereas in one orbital, if we have two electrons, then spin of that orbital is zero. So that means when we have paired electrons, then what happens? Spin also decreases. So that's why this magnetism of complex compounds here is calculated in terms of number of unpaired electrons. Why? Because this spin quantum number is purely depends on the number of unpaired electrons. So that's why this magnetism of complex compounds is generally calculated in terms of number of unpaired electrons instead of spin quantum number and spin of electrons. So therefore, we have one magnetism formula. What is the magnetism formula? Mu s. That is magnetism of complex compounds, or magnetism is denoted as mu s. So mu s is equal to square root of n into n plus 2, where n is what? Unpaired electrons. Number of unpaired electrons. Mu is magnetic momentum or magnetism. Okay, no problem. And next, see now on the basis of magnetic momentum. So magnetic momentum means that is mu value. So if any molecule or complex compound in which if n is 0, so that means if it doesn't have any unpaired electrons in its outermost shell, then such complex compounds are termed as diamagnetic in nature. So that means the magnetism of those compounds is 0. Magnetism, or you can say magnetic moment. Whenever n is equal to 0, then what happens? So if you substitute n value in that formula, what is that? N square root of n into n plus 2, you will get what? 0 value. So 0 means magnetism is 0. So such compounds are denoted as diamagnetic. Next, paramagnetic. So if any complex compound which has more than one unpaired electrons in its outermost shell. So what are para? The generally para compounds which may have or which possess or have more than one unpaired electron in its outermost shell. Okay. So such complex compounds are known as paramagnetic. So for example, here he calculated two values. So if n is equal to 1, then magnetic moment is how much? 1.73. These Bohr magnets are the units for magnetism. Okay. If n is equal to 3, then it will be 3.87. If n is equal to 2, then that will be 2.78. Okay. So you can substitute this n value in this formula. You will make it different value. So maximum, how many unpaired electrons we may have in outermost shell d subshell? 5 unpaired electrons. Okay, beyond 5 we don't have. Why? Because if the sixth electron, what happens? The sixth electron starts pairing up. Okay, sixth electron onwards, what happens in the d subshell? Electrons will be paired up. Okay, so maximum, how many unpaired electrons we can expect in d subshell? 5. Okay, more than that we can have. Okay, next. Let's see some examples. Here, see nickel. So the nickel, what is the atomic number of nickel? 28. And what is the outermost electronic configuration of nickel? 3d8 NH2, NP 0. 3d8 NH2. Before that, we have nickel, argon. Argon atomic number is 18. 18 plus 2, 20. 20 plus 8, 28. So atomic number. So here, see, in previous classes also I told you that the calculation of oxidation state of central metal atom is very, very important. Without that, we cannot calculate the EAN or assign the EAN, calculate the effective atomic number or number of electrons of complex compound, and it is not possible to tell the oxidation state in nomenclature. Whereas in VBT also, without knowing the oxidation state, we cannot predict actual geometry or shape or actual hybridization of complex compounds. So you should be good at calculation of oxidation state of central metal atom. Okay. See, now in this complex NaCl4 minus 2, in this complex compound, the oxidation state of nickel is N plus 2. So in N plus 2, the outermost electronic configuration is 3d8, 4s0, 4p0. So why? Because in nickel we have 3d8, 4s2, and in nickel plus 2, what happens? These two 4s electrons are removed. So thereby this 4s becomes as empty, 0. Next, again, see this chlorine. It is a weak field ligand. So weak field ligand do not pair up electrons. So this is chlorine is a weak field ligand. So that's why here what happens in outermost shell, we have two unpaired electrons. And next, this nickel is going to taken up how many unpaired electrons? how many lone pair of electrons from ligand, or we can say coordination number also. So here the coordination number is 4. That means nickel has to provide how many vacant orbitals? 4. So here see 1, 2, 3, 4. So out of 4, 1 from s orbital and 3 from p orbital. Now this what happened? This singular energetic orbitals undergo hybridization. So and that hybridization is known as sp3. And now this sp3 hybridized orbital overlap with the ligand. So after overlapping, here he shown two dots. So two dots indicates what? These two, this vacant orbital is filled with two electrons. So those are donated by whom? Ligand. Next, see, the hybridization is sp3, and as for sp3 hybridization, we can say that what is the geometry? We can say that as tetrahedral. You know that. And next, in the outermost shell, we can explain another property, that is one paramagnetism. Magnetism. So in outermost shell, it has how many unpaired electrons? Two unpaired electrons. So the complex compound or complex which has more than one, unpaired electron, that is what? Paramagnetic in nature. Next, look at next example. NaCN4 in square bracket. What is the charge? +2. So if you calculate the oxidation state of nickel, again you make it Ni+2. So what is the uh, electronic configuration of Na+2? That is 3d8, 4s0, 4p0. But here see which ligand we have. We have strong field ligand. So what is the nature of strong field ligand? So this strong field ligand will pair up this electron. So they shift this electron from this orbital into this orbital. So then that provides, thereby it provides one vacant d orbital. So now this d orbital become vacant. So next, what is the coordination number of this complex? Complex 4. So that means this nickel has to provide how many vacant orbitals? 4 vacant orbitals. One is the d orbital, one from d, one from s, and two from p. So how many total? 4. And what is the hybridization? So one d orbital, one s orbital, and two p orbitals. And the hybridization is dsp2. So see, here also nickel need to be provided 4 vacant orbitals. In second case also it required to provide 4 vacant orbitals. But here see, here the 4 orbitals are from 1s and 3p. But in second case, these 4 are vacant orbitals are from 1d, 1s, and 2p. So why this difference? Because of the nature of ligand. So what is the nature of strong field ligand? It pair up the electrons, unpaired electrons. Pair up strong field ligands, pair up the unpaired electrons, thereby providing vacant d orbital. Okay. So which d orbital? Is it inner d orbital or outer d orbital? Obviously it is inner. Inner why? Because it is 3d. And what is the principal quantum number of outermost shell? 4. And principal quantum number of inner is 3. So 3 means it is inner, inside of outermost shell. So that's why this hybridization is known as inner hybridization. And this inner hybridization result, which type of spin of complex compound? Low spin. Why low spin? Why? Because if electrons are paired up, then spin is 0. Okay. When we can expect this spin? Spin is nothing but spin quantum number. So if electrons are unpaired, at that time we can expect the spin. In first case, we can expect spin. Right? So this is plus of and plus of. So how much? Plus of plus of. How much? 1. But here what happened? All electrons are paired up. So in each orbital, the sum of spin quantum number is 0. Why? Because this is plus half and second one is minus half. If you summate it, if you add it, plus half plus minus half, how much? 0. So 0, 0, 0, 0. But here 0, 0, 0. Here plus half and plus half. How much? Plus half plus half 1. Next, this is inner hybridization. And what is the hybridization? dsp2. And what is the shape of dsp2? Square plane. And next, one more important thing is what? Magnetism. So here see, in outermost shell, if you look at the outermost shell here, so all electrons, how many electrons actually we have? 8 plus 8. How much? 16. All these 16 electrons are paired up. So that means we don't have any unpaired electrons. So that due to that, this complex compound XP, which magnetism? Diamagnetism. In next third example, see. So this is with new weak ligand, weak field ligand. This is with strong field ligand. And in first two cases, nickel resides +2 charge. But in this case with nickel carbonyl, or tetracarbonyl nickel, here the charge of nickel is 0. Why? Because carbonyl is a neutral ligand. We know that. Again, what is the coordination number 4? Again, it's required to be provided how many vacant orbitals? 4 vacant orbitals. Okay. But what is the nature of carbonyl? Carbonyl is a strong field ligand. Got it? So nickel. So how many electrons do it has? 28 electrons. So 4s2 3d8. And what is the nature of this carbonyl? It is strong field, and it can pair up the electrons. So these two s electrons are shifted into the d orbital. So thereby, by means of that, this s orbital became vacant. So how many vacant orbitals we require? 4. One is s and 3 from p. And what is the hybridization? sp3 hybridization. Then what is the shape? Tetrahedral. How many unpaired electron does it has? 0. So what is the nature? Damage. Okay, next, nickel can form coordination number of 4 and coordination number of 6 compounds. So up to now we have discussed about the coordination number 4 of nickel complex compounds. And next now we are going to discuss about the coordination number 6 of nickel complex compounds. So the example is nickel NH3 taken 6 times plus 2 charge. So in this case, what is the charge of nickel? Obviously plus 2. What is the outermost electronic configuration of Na plus 2? That is 3D8. So how many electron does it has? 8 electron in the outermost shell. So but whereas this ammonia is belongs to weak field ligand, so this weak field ligand do not pair up this electron. Next, what is the coordination number of this complex? 6. So that means nickel has to provide how many vacant orbitals? 6 vacant orbitals. So here see, inner d orbital, we don't have any vacant orbital, so that means we should have all vacant orbitals from outermost shell. So that is 6, 1 from S, 3 from P, total 4. And how many we require? 2. So those 2 will be accompanied, provided by 4d orbital. So and next, what is the hybridization? sp3d2 hybridization. And this sp3d2 hybridization is which type of outer hybridization? So okay, outer hybridization. Here see, here written as outer. Okay. Next, what is the shape? Octahedral. And another property we can know from this VBT theory is magnetism. And here, how many unpaired electrons does it has? 2 unpaired electrons. So that the magnetism is paramagnetic. And next, come to next compound, that is nickel, manganese. After nickel, we are going to study about manganese. As like nickel, manganese also exhibit two different coordination number of complex compounds. As one is as 4 and second one as 6. So in first case, the coordination number of the nickel is 6. So that means nickel has to provide how many vacant orbitals? 6 vacant orbitals. And in this case, what will be the charge of nickel? Manganese, Mn plus 2. So what is the atomic number of manganese? That is 25, and manganese outermost electronic configuration is 3d5, 4s2. But here what we have? Plus 2, that means 2 electrons from S been lost. So how many remain? 5 electrons are remained in 3d. And next, what is the nature of ligand? Strong field ligand. So what is the nature of strong field ligand? It pair up the electrons. So 5 electrons are paired into 2 sets and one remain one set. So this pairing provide two inner d orbitals. Inner d orbitals. So now we require how many vacant orbitals? 6. So out of 6, 2 are d, 2 are from d, 1 from s, and 3 from p. So what will be the hybridization? D to sp3. So here see D to sp3 we mentioned as inner. In the previous case, outer. Why outer? Outermost d orbital is participated in hybridization, and in this case, inner d orbital is participated in hybridization. So that is the difference between these two. And shape, shape or geometry as like previous octahedral. And next, how many unpaired electron does it has? 1. And what will be the nature? Magnetism, paramagnetic. And next, second example is MnCl4 minus 2. So coordination number of this complex compound is 4. That means manganese again has to provide how many vacant orbitals? 4 vacant orbitals. And what will be the charge? Mn plus 2. What is the electronic configuration of Mn plus 2? 3d5. But whereas we have Cl as a weak field ligand, so this weak field ligand cannot pair up the electron. So weak field ligand cannot pair up the electron. So at that time, so nickel need to be provide four vacant orbitals of outer shell, that is 4s and 4 no, no 4s and 4p, one from s and three from p. And what will be the hybridization? sp3 hybridization, and this is sp3. And what is the shape? Tetrahedral. And see here, see in such case only we can expect maximum number of unpaired electrons per. So this d black we can say transition series elements, the maximum unpaired number of electrons are 5 only. Above that we cannot expect. Why? Because sixth electron will be paired up. Okay, so maximum unpaired electrons 5. So what will be the magnetism? Paramagnetism. And this complex compound has highest magnetism. Why? Because it has highest unpaired number of electrons. Next, and very important one is the complex compounds of copper. Copper can also give coordination number of 4 as well as coordination number 6. But here the important one are these two, 4 complex compounds. So the copper atomic number is 29 and the outermost electronic configuration is 14 and 4s2. But here in these two cases, the oxidation state of copper is +2. So that means these 4s electrons are removed or eliminated. And what is the general electronic configuration of Cu+2? That is D9, 3D9. So this is 3D9, 4s0, 4p0. In both are coordination number 4. In both cases, copper required to provide 4 vacant orbitals. Okay. So in first case, this chlorine is a weak field ligand, so that's why it 4 1s and 3p orbitals are intermixing or hybridizing results a tetrahedral geometry, and then it had one vacant unpaired electron, so the magnetism is paramagnetism. In next case, see, in presence of copper, which one? Ammonia ligand in presence of copper, or chromium also sometimes, but majority cases copper. In ammonia in presence of copper, it acts as a strong. But see, already ammonia we have seen in case of nickel. But in nickel, with nickel, this ammonia acts as a weak field ligand. But when it with copper, it acts as a strong field ligand. So what happens? See, this ammonia, ammonia has shifted this 3d electron into p orbital. So this d electron into p orbital. Okay, why? Why? Because due to its strong field nature. So thereby it provide one vacant d orbital and one s orbital and two p orbitals. Why? We require only 4 vacant orbitals. So in first case also we require 4, but this chlorine doesn't promote or shifted this unpaired electron from d orbital into p orbital. But whereas this ammonia is shifted or transfers this d electron into 4. So thereby providing inner d vacant orbital. So now this inner d orbital, 1s orbital and p orbital. So these 4 orbital undergo dsp2 and results sphere planar. Magnetism is same. Okay. So you will do it remaining this, and in next class we will discuss about magnetism. So it will be our last topic of the coordination compound. After coordination compound, we have small lesson, that is boranes and nitrines. With this, we will complete our first unit. Okay. So thank you.